Okay, this will be the lecture for chapter 26. I'm going to start talking about some properties of light. And I kind of finished off where we start off right here last time. And I'm going to talk about electromagnetic waves, how we can have a changing electric field and a changing magnetic field. And we're going to call this thing an electromagnetic wave, abbreviated EM, electromagnetic. I'll talk about the frequencies, the electromagnetic spectrum, if you will. Talk about AM radio, FM radio, light, and how these guys are all electromagnetic waves, but how they're slightly different. I'll talk about what makes a material transparent, what makes it opaque, and how light slows down as it goes through mediums. And I'll finish off by talking about how we can see light, how we perceive this creature called electromagnetic waves, and light is an electromagnetic wave. So this is kind of where I finished off. I said if I had an antenna and I put this electron on this thing right here, then the electric field is going to point towards it. So there's my electric field. And if I were to wiggle this thing down, then my electric field is going to point down. And if I were to wiggle this thing up, then my electric field is going to, at some later time, point up. And you can picture me making this thing point up and down, up and down, up and down, up and down like this. So I'm going to have my electric field, and I'm going to have this changing electric field. A changing electric field is going to induce a magnetic field, and that magnetic field is going to be going up and down, actually with the same frequency. The frequency of the magnetic field is the same as the frequency of the electric field. Then we're going to have this, as I call it, self-feeding beast, and we're going to have this changing electric field, changing magnetic field, changing electric field, changing magnetic field, and so on and so forth. Somewhere over here, I'm going to maybe have an antenna. And this antenna is going to have some free electrons. Antennas are largely made out of metal. And what's going to happen is when this guy gets over here, it's going to start to drive this electron. Probably not surprisingly, this electron is going to start to go up and down, up and down, up and down, and it's going to be at the same frequency that we drive it. So when you tune your radio, essentially that's what you're doing, is you're saying, hey, look for this frequency of the electrons that are wiggling up and down. We call this thing an electromagnetic wave. Now, electromagnetic waves are actually going to be, in some sense, light waves. We can't necessarily see all of these frequencies. We can see some of them, but not all of them. So what it is essentially it's going to be this electric field. And the electric field is going to be going up and down, up and down, up and down. It's going to cause this magnetic field. The magnetic field is in green. And it's going to be going side to side, side to side, side to side. Don't worry too much about the direction. That's a bit beyond where we're going to talk about in Physics 102. But you can kind of see we have crests and we have troughs, and everything that we learned about mechanical waves can actually apply to electromagnetic waves. We can talk about things like the amplitude. We can talk about the peak-to-peak or the trough-to-trough distance. We can call that the wavelength, going to look like this. We can also talk about the wave speed or the wave velocity, and it turns out that it's also perpendicular to the two of those. All electromagnetic waves in a vacuum are going to propagate at one very special speed, and this is actually going to be the speed of light. It's abbreviated by a little c. The speed of light is very, very, very fast. It's 3 times 10 to the 8th meters per second. You definitely want to know what this guy is. Electromagnetic waves are a little bit different than mechanical waves in that they don't require a medium to propagate. Mechanical waves, like sound waves, they needed some air to pass it from one place to the next. Electromagnetic waves don't need that. Essentially what they have is they have the electric field, they have the magnetic field, that's all they need. So it can go through, say, outer space, which is essentially a vacuum. Light can go from the sun to here, and that's a good thing. It doesn't need anything in order for it to go through it. Some of the things that we learned about mechanical waves still apply. We have our old friend, speed is equal to wavelength times frequency. Kind of abbreviate this guy like this. Speed is equal to wavelength multiplied by frequency. This is going to apply to mechanical waves as well as light waves, but bear in mind that this speed right here is actually going to be the speed of light. Again, 3 times 10 to the 8th meters per second. Definitely want to know what that guy is. Let's just get a little bit of practice here calculating some frequencies. Let's calculate the frequencies of 532 nanometer light. One thing to bear in mind is we're going to start to see some different prefixes, and one of the prefixes that we see right here is nano. A nano is times 10 to the negative 9th. And this is visible light. It's actually in the greenish color. what we can do is we can say, well, what I've given you right here is I've given the wavelength, and the wavelength is going to be 532 times 10 to the negative ninth meters. That's what that little nano means. So let's just go ahead and really quickly do a calculation here. I'm looking for the frequency, so I can say the frequency is going to be equal to the speed divided by the wavelength, and this is going to be 3 times 10 to the 8th divided by 532 times 10 to the negative ninth. Now, one thing to bear in mind is as you type this into your calculator, please use more parentheses than you think that you should. And the reason for that is because a lot of times people type in 532 multiplied by 10 to the negative ninth. So just be careful as you do that. Now, I do encourage you to type this into your calculator and make sure that you get the same answer that I do, just that way you can do that. That way you're sure you know that you're typing into your calculator correctly. What you should get is you should get 5.639 times 10 to the 14th, and it's going to have a unit of hertz. Again, make sure you get the times 10 to the negative 14th. That's what people tend to mess up with the most. Now, let's just get a little bit more practice doing this and some practice kind of recognizing what we're looking at. If I have an electron and it's going to vibrate up and down 100 times each second, what can we say about the period, speed, or wavelength? Well, let's go ahead and calculate the speed, or better yet, let's just state the speed. The speed is going to be 3 times 10 to the 8th meters per second. So we know that this guy is not going to be true. Now the question is are we looking at the period here? And just take a look at the units. Essentially, I'm saying 100 times per second. Or I could also kind of write this as 1,000 hertz. So it is not going to have a period of 100 seconds. Now let's just go ahead and calculate the wavelength. We know that the speed is going to be equal to the wavelength multiplied by the frequency. So we could say that the wavelength is going to be equal to the speed divided by the frequency. The speed is going to be 3 times 10 to the 8th meters per second. The frequency we can now recognize as 1,000, and we're going to have 3 times 10 to the 5th meters. So this one is actually going to be none of the above, but we've gotten lots of practice recognizing what we have in using speed is equal to wavelength times frequency. Now, I do want to talk a little bit more about electromagnetic waves, and more specifically the electromagnetic spectrum. It turns out that any moving charged particle, any wiggling electron, if you will, is going to cause an electromagnetic wave, but we can't see all electromagnetic waves. Light, visible light, is the only one that we can see, and I'll talk about the frequencies or the wavelengths that are involved in a little bit. But pretty much any time you wiggle an electron, you're going to get an electromagnetic wave. We know that radio waves exist, we know that microwaves exist. We can't see them, but we know that they're there. So we can talk about the electromagnetic spectrum, again, kind of abbreviate that, the electromagnetic spectrum. And this is essentially characterizing the wavelengths according to their frequency. And if you remember your old friend Roy G. Biv, that kind of describes visible light. So Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Essentially that's characterizing the visible light spectrum in the language of frequency. The lowest frequency is red, the highest frequency is violet. So in this case right there, our frequency is going up as we go from red to violet. Now, we do know that above violet, we're actually going to have UV, and think of UVA, UVB. These have higher frequencies. It turns out that higher frequencies also mean higher energies, and that's why UV can burn you and visible light cannot. If you think back to mechanical waves, the more I were to shake a slinky up and down, the higher frequency it has, the more energy it has. The same is true for visible light. On the other side of the spectrum, we're going to have infrared, which means below red, and it's going to have even less energy than red. So here's our UV, and again, that causes sunburn. If we were to kind of take a look at this guy in the language of frequency, we can see that there's some more regions to worry about, and you can kind of see that here we're wiggling it kind of slow, and then we get up here and we're wiggling really fast. Down here we have radio waves, and then we have microwaves, and then we're going to have the IR, and then we have our visible light. Above that we're going to have our UV, and then we have X-rays. Kind of makes sense. X-rays can penetrate skin and bone and stuff like that. And above that we're going to have gamma rays, which have an even higher frequency and even more energy. Now, here's kind of another picture of the electromagnetic spectrum. I like this one a little bit better. Again, frequency in hertz kind of increasing in this direction. And one thing to pay attention to is we're talking about things from 10 to the 6 hertz, about a million hertz, all the way up to 10 to the 21 hertz. So we're spanning this huge dynamic range in the language of frequency when we talk about electromagnetic waves. We can wiggle electrons slowly, or we can wiggle electrons fast. They're all still going to produce electromagnetic waves. We know that AM radio is different than FM radio. Here we have microwaves. Visible light actually is going to take up just a teeny tiny portion of the spectrum. And that's actually kind of humbling that we can only see this little teeny tiny sliver of this big, huge dynamic range. Again, we're going to over here have our infrared, visible light, UV, X-rays, and gamma rays. We can also talk about this in the language of wavelength. And what we can do is we can say, well, here we have frequency, and right here we have wavelength. And as the frequency goes up, the wavelength goes down. The reason for that is because the speed of light is 3 times 10 to the 8th. And as the frequency goes up, the wavelength has to correspondingly go down, such that the product is always going to be 3 times 10 to the 8th. Very frequently in the language of visible light, we're going to see the wavelength written in terms of nanometers. Again, a nanometer is times 10 to the negative 9th meters, and we're going to have our reds, orange, yellows, green, blue, indigos, and violets, so the Roy G. Biv of the world. Bear in mind that these guys are kind of subjective. Right over here it's kind of a blur between red and orange and yellow, and so on and so forth. Green is going to peak around 550 nanometers, and essentially what we can see is from about 400 nanometers all the way up to nearly about 700 nanometers or so. Now, something that's kind of interesting is if we were to look in the 300 to 600 megahertz range, mega is a new prefix, that's going to be times 10 to the 6. If we were to look in this range right here, you can see that it's actually quite crowded. And this is kind of where phones, amateur radio, and broadcasting are. And, the big thing is 3G, 4G, 5G, and television stations. TV stations take up a huge swath of this. And that's why television stations are essentially selling their real estate, if you will. Because the more that we can free up over here, the more we can have for our cell phones and stuff like that. So just want to do a quick little check your neighbor type of question and ask yourself which of these is fundamentally different than the others. The answer to this one is actually going to be a sound wave, and the reason for that is because this guy is going to be a mechanical wave. Light waves, radio waves, X-rays, all of these guys are going to be electromagnetic waves. Again, bear in mind mechanical waves needs a medium, and that makes it fundamentally different than the others. These guys do not need a medium in order to propagate.